Angular momentum remains. Next heading. Angular momentum remains constant. Angular momentum remains constant under a central force. Okay. Next heading. Angular momentum remains constant under a central force. Okay. From the relation tau, vector tau equal to d vector j upon dt equal to vector r cross vector f. Okay. From the relation we find that the torque acting on the particle is zero. And hence the angular momentum remains conserved. We find the torque acting on the particle is zero, and hence the angular momentum remains constant. Angular momentum remains constant. Okay. First point. Its position vector r equal to 0. Second point. The force vector F applied to it is 0. Applied to it is 0. But if vector r not equal to 0, and vector f force not equal to 0, the third condition that must be satisfied, vector j is constant. Vector j is constant. Okay. Third point. Okay. The direction of both vector r and vector f. Okay. Vector r and vector f. Okay. The direction of both vector r and f should be the same. Is that the line of action of the force passes through the fixed r reference point. The third condition is satisfied in case of central force which is always directed towards or away from the fixed point. Okay. Consider a particle subjected to a central force depending upon the distance from the fixed point. Such as force can be represented as vector f equal to function of r unit vector r. Okay. Where fr is some scalar function. Fr is some scalar function of the distance, and this is a unit vector along vector r. Okay. Along vector r. Okay. Given by unit vector r equal to vector r upon mod of vector r. Okay. But vector tau equal to dj upon dt equal to vector r cross vector f equal to r function of r unit vector r. This is the mark of fr function. fr vector r cross unit vector. Okay. Equal to fr vector r cross vector r upon mod of vector r, okay, is equal to 0, because vector r cross vector r equal to 0, okay. So torque acting on a particle, torque acting on a particle, under the influence of a central force, is 0, okay. Then tau equal to dj upon dt equal to 0. So vector j equal to a constant, okay. Hence the angular momentum hence the angular momentum of a particle under the influence of central force always remains constant, okay. Hence the angular momentum of a particle under the influence of central force is always remains constant. Okay, thank you. Isotropy and rotational invariance of space. Isotropy and rotational invariance of space, okay. Space is isotropic. Okay. If we move in any direction from a point, there is nothing to distinguish one direction from another. For example, if we keep a particle P1 fixed and move another particle P2 on the surface of a sphere with P1 as a center, the interaction energy between the two will be the same for all position of P2 on the surface of the sphere, okay. Isotropy thus means rotational invariance of the properties of free space. Isotropy means rotational invariance of the properties of free space, okay. The term rotational invariance of a space further implies that the potential energy of interaction between two particles is an invariant, does not change if a position coordinate of the both particles are rotated through the same angle about an arbitrary axis, okay. Good.